All right, this is topic 3 on the periodic table. So we've already talked a little bit about some things about the periodic table, and we're going to go over some of the reasons why it's, I guess, organized the way it is and some trends in it. This video here, I can't post it inside of the video, or I can't play it just because that will go against YouTube copyrights. So I'll post this video along with this lesson on the Google Classroom. It says the organization of the periodic table. The periodic table organizes elements according to a number of properties, including reactivity and mass. And the other day in class, we talked about how as it goes up the periodic table, things become heavier, I guess we can say. Things have more mass. And that's mostly due to the fact that, well, the higher you go up on the periodic table, the more protons there are. Protons have mass. So as you have more protons, you're going to have higher mass. Periods, so those are the horizontal rows, are organized, they organize elements according to their atomic number. Groups, which are vertical columns, organize elements according to the number of valence electrons they possess. So I just want to go over that for a second. Valence electrons, I don't know if we've used that word yet, but those are the electrons that are in the outer shell. So when we're looking at the Bohr diagram, we're looking at valence electrons in their outer shell. Those are those ones, the last circle that has the electrons. So those outermost electrons. Those are called valence electrons. Oops. Did not mean to do that. I was going to underline it. All right. All elements to the left of that thick black staircase that you can see right on this diagram right there, those are considered metals, while all the elements to the right are nonmetals. And then elements that border that staircase are known as metalloids. So they're sort of like a mixture there, but not really a metal, not really a gas. So that's staircase that goes along the periodic table. And I've mentioned that in class as well, but that's how it's distinguished. So there's a whole lot more metals on the periodic table than there is non-metals. So properties of them, well, metals are normally solid at room temperature. The only exception to that rule is mercury, which is actually liquid at room temperature. Metals normally are shiny with luster, and they are good conductors of heat and electricity. So metals can conduct electricity. They hold heat better than non-metals. Metals can be malleable, or most of them are pretty malleable, and ductile. As far as non-metals go, some gases or some are solids, but only one is liquid at room temperature. So this is all talking about at room temperature. The only one that's liquid at room temperature is bromine. So if you look at the periodic table, you might notice that at least on my periodic table, they have different colors. The letters, the symbols of our periodic table. If we look at bromine, see bromine there, it's in blue. And blue is telling us, if we go over here, that blue is a liquid. Red is a gas, so a lot of those things are gases at room temperature. And then black are solid. So if we go over to mercury, that's also liquid at room temperature, that Hg. So that is also something that you might see on some periodic tables, maybe not yours, just because it's all black, but it's something to take note of. So bromine and mercury. Those are exceptions to our rules. Metalloids, on the other hand, I got to keep going on nonmetals. Nonmetals, they're not shiny, they're poor conductors of heat, and they're brittle or not ductile. Metalloids, on the other hand, they are solid at room temperature, so there's no exceptions to any of that rule. They can be shiny or dull, so there's sort of that mixture in between. Some conduct electricity, but are all very poor conductors of heat, so they're not really the greatest at conducting electricity or heat. And they tend to be brittle as well and non-ductile, so they fall a lot into the non-metal category, but some of them have that conducting of electricity, which makes them sort of that in-between. All right. So some practice here, it says determine whether each of the following elements would be classified as a metal, a non-metal, or a metalloid. So the first one is sodium. I'm going to go back up to here. So for sodium is right here. It's Na, and you can see this on your periodic table that might actually have names. But Na, it's in that red part, which means it is a metal. So we would write metal here. Neon, on the other hand, neon is way over on the right-hand side. It is a non-metal, and if we look at our periodic table, it is a gas. And you might know that. You might know what a neon sign is, for instance. It's just a tube with neon gas inside of it. Copper, I hope we know without even looking that up that copper is a metal, but I will show you it on the periodic table. You probably at least remember like a penny, which has some copper in it. Copper is right here. It's Cu. So that is a metal. Our next one is chlorine. Chlorine is over right here, Cl. That is a non-metal. Ca, that's calcium. So right here, calcium is a metal. And that might seem weird to you to think like, oh, calcium is a metal. It's sort of it's not our typical definition of a metal. When we think of metals, we think of something really, I guess, shiny and something that might not be quite as crumbly, but we know that, and it's also in our water, for instance, but these are minerals that can dissolve in water, and they are still considered metals. And mostly because they don't look shiny, because when they're exposed to the air, they will oxidize really fast, which we'll probably get into more later on. Au, if you know what Au is, you would know that it's a metal. Where is it? It's right here. It is gold. So gold, you would know without looking at the periodic table that gold is a metal. Si is in that metalloid area, and Si is silicone. So silicone isn't a metal or a gas, it's that metalloid. And then K is potassium. And potassium is a metal. It's on the left side of the periodic table, right here. Okay, so again, potassium, if you were to see potassium, it doesn't look shiny, and that's because it normally oxidizes, and that means that it changes, oxygen reacts with it when it goes into the air, and it loses that luster, I guess you could say. So our chemical families that we have in the periodic table, there's different sort of organizations here. We've got alkali metals, which are this very first column. And those columns that we have, those are called groups. So our chemical families are normally put together as groups. I don't mean to be writing with the highlighter, but those are our groups. So yeah, alkalis are our first group, that first row there, our column. And alkali metals are extremely reactive. They are rarely found in pure forms because how easy they react with other elements. So that's what I was telling you about potassium, for instance. You're not going to find potassium in nature, and if you do, it probably has already reacted with something else. So pure potassium, very difficult to find, and I will link a video of how reactive these things are. But as we go down, this is the same for all elements, but as we go down the rows, the column, I keep on wanting to say rows, down that column, they become more reactive. And this first row is really reactive with water. So if we throw any of these things in water, pure ones with water, they're going to react. And I'll show you, or I'll post a video of that. I just got to make a note of that on, or I'll forget. Perfect. Alkali earth metals, those are less reactive than the alkali. So as we go this way, they aren't as quite as reactive. This group is, I guess, yeah, they're earth metals. They do react as well. As you go down, they become more reactive, but not quite as reactive as that first group. All right. Over on the right-hand side, we've got our noble gases, and those are really important here. Noble gases, they are I always say the coolest kids on the periodic table. They don't really react with anyone, and everyone wants to be like them. Saying they're the cool kids. So everyone wants to be like neon, argon, krypton, xenon, radon, and helium. And to be like them, basically why they're so cool is because their outer shell is filled up with electrons, so it's full. So helium, if we were to draw the Bohr diagram for that, it only has 2. Neon, if we were to draw the diagram for that, we would have 2, and then the next one holds 8. Well, that is full. So the reason why these guys are cool is because their outer shell is full. Right, so I'm gonna write that too. So their outer shell, which we called valence shell, is full. So all these guys, noble gases, they're the coolest. Their valence shell is full. And then the ones right before them, they are pretty close to being as cool as the noble gases, but they're missing 1 electron in their outer shell. They're known as the halogens. They are extremely reactive as well, just because they are sort of like at the breaking point. They're not quite to being as cool as the noble gases. And they are all gases at room temperature except for bromine, which is the exception that we went over before. All right. At the bottom here, it says all elements to the left of the thick line. Oh yeah, we already went over that. So don't need to say that again. Patterns in electron arrangement. Well, electrons are only subatomic particle. Electrons are the only subatomic particle that is exchanged between 2 elements when they react. An element's reactivity is directly related to the number of valence electrons it holds in its outer shell. So, like I said, everything, the most stable, most coolest kids on the periodic table are the noble gases, and everyone else wants to, they either gain or lose to be like them. An element's reactivity is really depending on how many they have in their outer shell. So lithium, it has 1 when it could have a total of 8. So that becomes pretty reactive. And that's because it doesn't have much to lose. So it doesn't need, I guess, as much energy to lose or to become like the noble gases. The group number in which an element lies can therefore be used to determine how many electrons it will have in its outer shell. Elements in each group or family have similar properties because they have the same number of valence electrons. So what it's saying here is that as we go down, or as we look at these groups, they have similar characteristics because they are in the same family. All right. They give lithium as an example. It's located in period 2, group 1, and it is therefore has 2 occupied energy levels and 1 valence electron. So that tells us a lot. So it's sort of like Battleship. We find lithium right here. Lithium is 2 down. Remember, the amount that it is down tells us how many circles there are, how many energy levels there are. And then how far over this way tells us how many electrons are in its outer shell. So if it's 2 down, it's got 2 circles. 1 in the first one, it has 1 in the outer shell. So the periodic table, I always told you, is going to tell you almost everything you need to know. So this question, some practice, says how many valence electrons does an atom of lithium have? So to figure out valence electrons, just want to remind us here, valence electrons are the outer shell electrons. And this can be figured out by counting left to right. On periodic table. Okay. So if we look at this question, how many valence electrons does an atom of lithium have? Well, it's on the very left-hand side. So we really are only counting over 1. So how many does it have? The answer is 1. How many valence electrons does fluorine have? They've actually, so this is abbreviated, you know, the space that's here, we sort of skip over that just because it's not, the transition metals is what it is. Those aren't as important to us, so we only are counting over at the top as well. So that's why this might look a little weird. But if we're looking at fluorine, we go, fluorine's right here. We go 1, 2, 3, 4, 5, 6, 7. So it's 7 over from the left, which means it has 7 valence electrons. Okay. Explain why the noble gases such as helium and neon are unreactive. So I just said that already, but why are they unreactive? They are noble gases. That's these guys. So why are they unreactive? Because they already have their outer shell is full. So the only reason elements actually react because they want to share or steal from other elements so that they can have their energy level full. Well, these guys are already full, so they don't need anyone to help them out. So that's why they are unreactive. So I'm going to say their valence shell is full. explained by alkali metals such as sodium and potassium are extremely reactive. So why are alkali metals such as sodium and potassium extremely reactive? Well, if we see where sodium and potassium are, they are ones that, if we were to draw sodium, it's got 3 circles. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And then because it's only 1 over, it has 1 in its outer shell. So because it only has 1, it's really easy for it to lose that and be stable, right? Stable is being full. So because that one is, and same as potassium, I'm not going to draw that one, but because they are not full, they are really easy or really close to being, I guess, a noble gas. They react extremely well. So extremely reactive because they are close to being a noble gas, I'm going to say. So just by losing that one piece, they can become a noble gas. So that one, if they got rid of this 1 electron, well, now they're stable. So that's why they're really reactive, because they're so close, they just want to get there to that, getting rid of that electron. So this leads us to something that we use called electron dot diagrams. And another word for this is Lewis structures or Lewis diagrams, which it says right there. These may be used to show the number of valence electrons an atom possesses. Elements with unpaired electrons are capable of reacting with other elements. Those with a single unpaired electron are typically more reactive than those with multiple unpaired electrons. So it gives nitrogen as an example. It has 5 valence electrons. So it says start by placing the first electron at the 12 o'clock position and then move clockwise, placing each subsequent dot at the next position, 3, 6, and 9. Once you return to the 12 o'clock position, you will have to begin to double up. So I'm going to show you what that whole means, maybe just up in the corner here. So if we wanted to draw the dot diagram for nitrogen, we're going to write the symbol for nitrogen, which is N. Then we're going to figure out how many valence electrons it has. And like I told you before, to find out valence electrons, we count left to right on periodic table. Okay, valence electrons, counting left to right on periodic table. So for nitrogen, we count left to right. Nitrogen's right here, so we're going to count left to right. 1, 2, 3, 4, 5. Good. We have 5 valence electrons. Okay, so now we know there's 5 dots. What it means by counting with your 12 o'clock and all that stuff, that means they're talking about a clock. We start up here. We start at the top and then we go clockwise, so to the right. So we have 5 to put in. We go 1, 2, 3, 4. And then once we've done all 4, we start to pair. So we put another one beside the one at the 12 o'clock position, as they called it. Okay, so that's what they're trying to represent right here. Their dots are not really close together. It makes it maybe look a little bit more confusing, but this is what they mean. Okay, so we're going to do some practice, and it gives us the periodic table to the right, which is really nice. So we're going to do beryllium. So beryllium is right here. It is Be. So we're going to write Be. Then we're going to figure out how many valence electrons it has. Sometimes people will make a mistake and they will go, well, it's number 4 in the periodic table, so it has 4 electrons. It does have 4 electrons, but we're only looking at the ones that are in the outer shell. So to figure out the outer shell, we just count left to right. So 1, 2. So there's actually only 2 on this one. We start at the top and we start going counterclockwise. That's 1, 2. That is beryllium. Sulfur is S. Sorry, I didn't show you. S is right here. So to figure out how many electrons we count left to right, 1, 2, 3, 4, 5, 6. So it's not 16, it's 6. We will just want the outer shell. Okay, so 6, start at the top and start going around. Once we've done our 4, we'll start to pair them. And it looks something like that. All right. So beryllium's right there, sulfur's right there, calcium I'm gonna put over here. Calcium is Ca right here. If we count over from left to right, we got 1 and 2. So we just put 2 dots. Start at the top and go clockwise. So notice that calcium and beryllium, they only have 2 dots. They're in the same row, column, so that makes sense. Every single one in this column is gonna have 2 dots. If I draw magnesium, Mg, it's gonna have 2 dots, all right? So whatever column it is in the periodic table, that's gonna tell you how many dots or valence electrons it has. Francium is right here. It's in the very first row, which means it only has 1 dot, 1 valence electron. So we put that at the top. Francium is extremely reactive. It's in that very first column and it's at the very bottom. We would never be able to have francium in our lab because it could blow up at any second. Tin is Sn. Tin is right here. So for counting left to right, we go 1, 2, 3, 4. It's 4 over from the left-hand side. And remember, when we're looking at tin, or if you're looking at your periodic table, all these, I'm gonna write it in here, the transition metals, you would have colored them a different color on your periodic table. We don't worry about those. So we don't look at those. They're not important in our counting, okay? That's why I'm writing them over in red. So don't worry about transition metals. They're not important. For tin, we were 4 over. So we're going to write SN 1, 2, 3, 4, okay? And then the last one is argon. Argon, I can do right down here. Argon is right here. It's Ar. And argon is 8 over. I know that without even counting because I know that argon is a noble gas and they always have 8 except for helium. It only has 2. But I'll count over to show you to argon. 1, 2, 3, 4, 5, 6, 7, 8. So if we were on argon, we would go 1, 2, 3, 4, 5, 6, 7, 8. So this is what a full cool kid on the periodic table might look like. It has 8 different electrons around it, and it's full. So anything that the maximum any can ever hold is 8. That's the maximum in the outer shell. So we're not too concerned about any of those transition metals when we're dealing with this, okay? Now looking at physical properties versus chemical. Elements that belong to the same family and have the same number of valence electrons tend to display similar physical and chemical properties. Any property that can be observed or measured without forming a new substance is known as a physical property. So the example is density. So density, when we look at water, water could be in liquid, solid, and gas, and we can see that in our life. Water is one of the ones that we can see, and that's basically a physical change, not a chemical. So even though there's liquid water here, and then there's solid water, which is ice, it's still water. It's not changing its property. It's still H2O. All right? That would be a physical property change. Any property that describes how a substance reacts with another substance is a chemical property. So an example of that might be flammable. So if something is to catch fire, that burning is creating a chemical change. Okay? So that example of burning is a chemical change. And this is because this burning will actually give off carbon dioxide, which is something that may not have been there before. But regardless, not important. Just know that, yeah, something that is becoming a new substance is a chemical change. And one of those ways is burning something or being flammable. So here are some properties that we can keep in mind when we're trying to remember if something had a chemical or physical or chemical or physical change. So some chemical properties are its reactivity with others, combustibility, stability, enthalpy of formation, so that's taking in energy. pH, so how acidic and basic it is, and then the toxicity. So some physical qualitative properties, these are things that we can see. So qualitative is seeing. These are color, texture, state, so whether it's solid, liquid, or gas, how malleable it is, so that means how we can bend it. And then how it smells. So if you see, or if you can smell something different, that could be definitely a physical property that you would write down. So solid, liquid, or a gas right here. And then our physical properties, which are quantitative. So quantitative is normally numbers. You can write down some sort of numbers. This is our boiling point, density, viscosity, solubility, conductivity, and mass. So these are all different physical versus chemical properties that we can have. All right, so now you can go and you can fill out or do the topic 3 assignment, and then we will start to do, or I will record the topic 4 lesson tomorrow, and you can try and work through that. All right, let me know if you have any questions, and I'll be happy to help you out.